if you're asked to find all the real and imaginary zeros for this polynomial, you can start with the rational zeros theorem. List all the factors of the first number. 1, 3, 5, and 15 all fit in evenly to the number 15. And then think about how you compare that with the factors of the first number. And the first number just is a 1 here. So when you pair all those up, I mean, everything's divided by 1. This is basically what you have, because dividing by 1 doesn't change it. You have these 8 options. It could be positive -1, positive -3, positive -5, or positive -15 for rational zeros. So if you don't have a calculator, you can just plug each one of those in. Start with positive 1, start with -1. Keep working until you find one that's a root. If you're not sure what a root is at this point, though, that root is just the thing that makes it be 0. And if you plug in those numbers again and again, you get, starting with that first list, -1 turns out to be a root. Plugging in -1 makes this whole thing equal 0. So here's what we're going to do. We're going to break this down into a smaller piece. We know that x plus 1 has to be a piece that can factor out of this. Because if -1 was a 0, then -1 plus 1 would make 0, and that would make everything else turn into be 0. This has to be in there. So by dividing out an x plus 1, it's like we're taking this, we're going to divide it by x plus 1. And the reason why we're going to do that is because it's going to make a smaller polynomial, one we might be able to digest easier to find the other 2 solutions. And by the way, there's 3 solutions because that's the highest power. -1's 1, so we've got to find the other 2. But yeah, we know -1, x plus 1 has to be a 0 because -1 is a 0. That's the only way to make that happen. So we got to find out what it looks like after we divide out x plus 1. So if x plus 1 is going to be a 0, then I'm going to use synthetic division, which is where I put -1 in the bracket, the root of my divisor, the thing that makes the divisor equal 0. And then you carry down the first number, you multiply these two, then you add the column. Then repeat, multiply those two, and add the column. Multiply those two, and add the column. You should always get no remainder if you're trying to factor out a linear piece. If you do get a remainder, it means you either messed up synthetic division, or you messed up choosing your linear piece. So here's what's left over. We started with x to the third, so now we have 1x squared minus 2x minus 15. So with synthetic division, the power is always reducing after each step. So here, you could use the quadratic formula right now and find the other 2 zeros for this polynomial. Or, this is actually something we can factor, I think. 2 numbers that multiply to be -15, but add it to be -2. How about -5 and +3? -5 times +3 makes -15. -5 plus +3 makes -2. So I took this and I factored it. And now, look, I took this big, long polynomial and I changed it into this. When you have everything factored in an equation, it's easy to find the zeros. You just set each parentheses equal to 0. X equals -1 is one of our zeros. X equals 5, and x equals -3. Those are our roots for this problem.